Okay, welcome to this morning's session. We have 2 talks before lunch during this session. And so the first talk of the morning is a tutorial by Helena Reichlova from the Czech Academy of Sciences, and she'll talk about spin transport experiments in altermagnets.
So thank you for the introduction. Thank you for the invitation to the wonderful workshop. I mean, I'm very sorry that I could not be there in person, but I'm happy that I can join at least online. And so today I will talk about spin transport experiments, which we do in these altermagnets, which were also introduced extensively yesterday. But before that, I also wanted to kind of summarize a little bit spin transport in compensated magnets in general. So as it was said, I am Helena Reichlova. I am currently working in the Institute of Physics in the Czech Academy of Sciences. However, as an experimentalist, I work in rather broad collaboration, and you see that there are people, also familiar faces, which are present today at the workshop. And next to my group, there is many people which somehow work together with us. So let me now move to just single slide motivating why to go through all the difficulties in working with these compensated magnets in general. And this brings me to this spintronics with antiferromagnets, which is now already established field growing in, let's say, last 2 decades. And it started, let's say, by general curiosity, right? Why we are sort of working only with the uncompensated system with the net magnetization. However, there was also, let's say, application aspect in that question. And this comes to this kind of very sort of simplified table, which compares the ferromagnets and compensated magnets, some of the fundamental properties of these classes. And we all know that there is the stray field present in the ferromagnetic systems, which, let's say, complicates the integration, how close we can put the 2 elements together. However, there are also some other aspects, and for example, the intrinsic frequencies, the frequency, how fast we can basically reverse magnetization in ferromagnets is limited to these gigahertz regimes, which is compared to slower compared to compensated magnets in general in this terahertz regime. And also the, let's say, choice of materials, the materials which nature basically gave us, is relatively limited when we stay in the ferromagnetic regime. So, for example, the search for ferromagnetic semiconductors was very active area of research when I did my PhD. And it turned out to be not so trivial that basically the ferromagnetic and semiconducting properties do not like each other. And it's a completely different story in compensated magnets. So there is many antiferromagnets or altermagnets, which are intrinsic semiconductors. So simply this aspect that we have the full playground of all the electronic properties available in the compensated systems, I think is also very important motivation for understanding the spintronic or spin transport in these antiferromagnetic systems. But next to this, of course, there are also some challenges, and these challenges are connected to this absence of the stray field and to this insensitivity, relative insensitivity to the external field. And there are ongoing questions how to simply couple to these compensated systems, how to reverse them, how to control them, and also how to detect them. So, so simply this could be wrapped up in a question. So can we have something like this most of, let's say, well-known spintronic phenomena such as GMR in compensated magnetic system? So let me now go through, let's say, some effects, like the key effects, hallmark effects of spintronic, and what we basically know about antiferromagnets, if they do exhibit these effects, and how it can happen that they exhibit these effects. So probably one of the most simple and well known already since, let's say, Lord Kelvin, and all these times where they had a piece of ferromagnetic material. Then we know that there is anomalous Hall effect, which basically refers to transversal voltage, which is detected perpendicular to the current and some magnetic order parameter. And this anomalous Hall effect was historically considered to be proportional to the net magnetization, to be present only in the ferromagnetic metals. However, there was a very inspiring history happening, and already when I did my PhD, there started to be some, let's say, hints that actually the anomalous Hall effect has components which do not need to rely on the net magnetic moment. And indeed, in 2015 and 2016, the group of Professor Nakatsui and Professor Felser showed that the anomalous Hall effect can be present also in materials without net moment, so that it does not rely on the net magnetic moment, does not need to be a ferromagnet to exhibit the anomalous Hall effect. And basically since then, this is now, let's say, 10 years, it became rather common. There are many materials, full families of materials of antiferromagnets which do exhibit the anomalous Hall and the thermal electric counterpart anomalous Nernst effect. And it all comes to these intrinsic contributions to the anomalous Hall effect, which were also discussed yesterday, that simply allow for the existence of the effect. So this was the anomalous Hall effect, and then maybe more, let's say, from the application perspective, better known effect is the tunneling magnetoresistance. So tunneling magnetoresistance in principle refers to effect where there are two layers separated by an insulating barrier. And here I intentionally put two cartoons to show, let's say, two variants of this tunneling magnetoresistance. One of them being this one layer of a magnetic material, and on the other side a non-magnetic electrode, for example, platinum. And in this configuration, in this experimental configuration, the tunneling magnetoresistance relies on the anisotropy of the ferromagnetic or generally magnetic electrode below the insulator. Sometimes it's referred as a tunneling anisotropic magnetoresistance. And this effect is typically not very large, but it can in principle exist. The second one, the widely used and explored, is the classical variant where we have two ferromagnetic electrodes or layers separated by an insulating barrier. And this is the one which is so heavily used in industry, and this is the one which is optimized to exhibit these huge ratios. And so during basically let's say last 15 or 20 years, it was shown that this tunneling anisotropic magnetoresistance can be present also in compensated systems. And this was work which we did already a long time ago, but in principle it relied on a fact that material, antiferromagnetic material, in that case it was iridium manganese, can kind of exhibit some sort of anisotropic magnetoresistance. And so then the anisotropic magnetoresistance of this layer and is then detected through this insulating barrier in this non-magnetic material such as platinum. And indeed, it can exhibit resistance behavior depending on the orientation of the iridium mangan or the antiferromagnet here on the bottom. So here is an example of such a measurement in iridium manganese platinum. And one can see that the characteristic like spin valve-like signal was observed. The difficult part on this particular is that, as I said, the signal is very small, therefore very, and there is not much space for improvement, the signal. And also that one has to find some sweet spot where this electrode can be sort of reversed partially to get some sort of anisotropic signal. So this was status, let's say, a couple of years ago, and last year or 2 years ago, there were two, I think, very important papers which showed that in two antiferromagnetic electrodes separated by an insulating barrier, one can indeed measure full antiferromagnetic tunneling magnetoresistance by these two groups, which again, I think it's a very big step for the antiferromagnetic spintronics. And the last thing which I want to mention, one of the, let's say, hallmark effect of spintronic research is the gigantic magnetoresistance, which is basically equivalent of the tunneling magnetoresistance. However, in this case, we have a more simple structure and we rely on a non-magnetic conductive spacer, such a copper. And here then we really probe directly the, let's say, spin polarization, which comes from one magnetic layer and how is it deflected or absorbed in the second magnetic layer. And this gigantic magnetoresistance effect was explored theoretically in antiferromagnetic systems. There is a beautiful paper of Jakub Železný and so on. However, experimentally, to my knowledge, there is no evidence of this gigantic magnetoresistance in antiferromagnet. And very often it comes down to experimental difficulties related to the quality or to the perfect interface and to the relatively low spin current coherence that one loses the spin polarization which is required to get like a measurable signal. So experimentally this part is basically missing. So when I now kind of have these three, let's say, effects next to each other, although not all of them were already experimentally demonstrated, but nevertheless there is an amazing amount of work done and still ongoing. And you see that one thing which, let's say, makes it common, so that in the antiferromagnetic spintronics, these systems, not the most simple collinear systems, but the systems which are having some, let's say, a little bit more complicated structure, either this triangular or some non-collinear, non-coplanar. So this became, to some extent, workhorses of the antiferromagnetic spintronics. Mangan-3 tin is a fascinating material, mangan-3 platinum. So all these effects were, in fact, observed or studied in these non-collinear systems. And before I go to these collinear systems, where you probably already know where I'm heading, let me just make a small excursion to also the, let's say, spintronics with collinear antiferromagnets. And this brings me to a very special class of materials. So in a conventional collinear antiferromagnets, the phenomena such as anomalous Hall effect, TMR, GMR, or the effects which rely on a spin coherence, they are not allowed. So the anomalous Hall effect simply relies on some time reversal breaking in the electronic bands, and since the bands are degenerate in these collinear systems, these are not allowed. However, in the collinear systems, there exists a class of materials which are having locally broken inversion symmetry, such as, for example, copper-mangan arsenide or mangan-2 gold. And in these materials, a lot of fascinating things were demonstrated. And probably the most important one is that these materials can, because of this, let's say, staggered effective magnetic field, can be electrically switched. That the magnetic order vector, the null vector, can be switched by electric pulses. And this made the copper-mangan arsenide and the related family of material very much explored and studied, and there is a lot of very important research going on, which again is related to what I said about antiferromagnets, that they can operate in the terahertz regime, that they can do all this also neuromorphic-like functionality. So all that is being explored in copper-mangan arsenide. And one more thing, which I think now is just a side note, these effects are also not showing only the switching, which I am showing here, but also they are kind of sensitive to second or because this kind of broken symmetries, they allow for second order effects. So what we, for example, showed here is that even when one kind of flips the null vector in this material fully to this like 180 degrees, which in principle should not give rise to the signal in the first harmonic, we can detect the switching in a second harmonic in this sort of nonlinear effect, exactly because of this particular symmetry uh, uh, experiencing, let's say, a different let's say effect when the electrical current is sent in one direction and the opposite. So there is this kind of asymmetry when the current goes in one direction and the other direction, which allows for this nonlinear effects. And yes, this is also where these materials, I think, now are discussed, and I think it's also a very exciting direction of research. So this was a small recap, let's say, of the spintronics with the antiferromagnets, or with what I understand as antiferromagnets. And when we now stay in the, let's say, realm of the collinear systems, then I already get to slide, which you saw a few times during this workshop. And just very quickly to recap, so what I mean here is that with the collinear systems, when we forget about spin orbit interactions, when we just look at the most simplified model, we can say that ferromagnets are the systems which we like because they exhibit this large splitting between spin up and spin down in the electronic bands. In these collinear systems, such as the copper mangan arsenide, which I showed before, the spin up and spin down bands are degenerate, not allowing therefore for effects like anomalous Hall effect, but nevertheless allowing for many other interesting physics, which I mentioned in the previous slide. And then, as Libor and Tomáš and Jairo showed, there is additional class of magnetic materials, and they simply arise from the fact that one does not consider only this simple like a lattice of basically arrows being antiparallel to each other, but one also considers, let's say, the non-magnetic environment, if I say it very simplified. And this non-magnetic environment here could be either, let's say, oxygen or tellurium cages. I will discuss it then later in some particular material candidates. But it can be also the underlying crystal structure. So this is another candidate which I will discuss. So the non-magnetic part of the crystal is the thing which then allows for breaking of the time reversal symmetry in the electronic bands, which from the real space translates to the momentum space as this characteristic alternating spin splitting. So we still maintain the full compensation. However, if we look in some particular crystal direction, we see the splitting between the spin up and spin down band. And what is the important thing here is that the magnitude of the splitting is not like some small correction of some sort of Rashba type splitting. It's order of the ferromagnetic materials up to like 1 electron volt and so on. So the second important point which I want to mention is that here the character of this collinear system also then translates as a spin up and spin down being conserved, being good quantum numbers, and therefore it in principle also allows for more robust, let's say, spin coherence, spin current generation, and so on. So when I come back now to the cartoon, we have a class which to some extent combines the properties of ferromagnets and antiferromagnets. However, it also offers features beyond both of these classes, such as, for example, this anisotropy. So that's something which is, let's say, not existing in any ferromagnet, that depending on the crystal direction, the spin polarization of the, let's say, charge current would be alternating. So this sort of anisotropic character is something which is simply even not only combination of ferromagnets and antiferromagnets, but it goes simply beyond. And again, important for experimentalists, these materials are not some obscure compounds where one or two were identified, but they are now full catalogs, also with many people from this workshop worked on that, which list like many of these altermagnetic materials. And because of Libor's nice symmetry classification, one can relatively easily identify more and more of these materials, and they are at least as abundant as let's say ferromagnets in nature. So it's like a significant family of materials, and therefore I think that it deserves its special, let's say, category of let's say magnetic ordering. So now when we went through this introduction, let me go to some already concrete materials which fulfill these altermagnetic symmetries. And as I said, that they are ranging from basically metallic systems to semiconducting to insulating. So I choose here a couple of materials which we study in our group. And yes, and then I will focus on some of them depending how the time goes. And in this slide, I just want to show that there are basically multiple ways how to break the symmetries, how to kind of use the non-magnetic environment to get the altermagnetic symmetry. And probably the let's say the model or the best known structure or cartoon is this D-wave system, this ruthenium dioxide related materials, where the magnetic atoms are surrounded by these oxygen cages, and then one can see that by flipping this arrow, one cannot simply translate or by inversion recover the original image. So there is a rotation of the crystal lattice needed. Therefore, this is the most probably well-known way how to get the altermagnetic symmetry. However, there are also a little bit more complicated cases, such as, for example, mangan telluride, where again the tellurium cages are rotated with respect to each other, but also they are sort of, it's a combined rotation and translation. It's some sort of screw symmetry, but again, this together allows for breaking of the corresponding symmetry. So this is another altermagnet well known already. And also the mangan 5 silicon 3, which I will also mention during the talk. Here it's not directly the non-magnetic atoms, their positions, but this is the underlying lattice. So the change of a lattice from, let's say, tetragonal to hexagonal already allows for the breaking of the symmetries, and then this material also is then allowing for the altermagnetic effects. And then there is a large family of materials which are even more complicated. And this is, for example, material which is prepared in Dresden at Leibniz Institute. And you see that here this spin are surrounded by this sort of canted octahedra with respect to each other. It's maybe not easy to see on the first look, but again, this complicated, relatively complicated material compounds, they are very often actually helping us that they are altermagnetic because they have some sort of breaking of the symmetries, that these two are sort of having different, experiencing different the crystal environment. And so how to basically test the spin transport in these altermagnetic systems. So in this, let's say, conductive materials, what we can easily do is to test it via this most simple effect, which I showed before, the anomalous Hall effect. In this insulating system, what we decided to do is to explore so-called spin Hall magnetoresistance, which, if time allows, I will also try to describe in more details. So since I said that we are using the anomalous Hall effect as like transport tool to test the presence of the altermagnetism. Let me just very briefly say what the anomalous Hall effect refers to, and why we basically think that it's a good tool to test the presence of the altermagnetism. I already said that it's an effect which generates transversal voltage perpendicular to the magnetic order vector and a current. And it was before thought to be only in the ferromagnets. Lately, the last 20 years, we also know that it's in non-collinear antiferromagnets. However, in the collinear one, it's simply forbidden by symmetry, right? Because this is an effect which relies on the time reversal symmetry breaking in the electronic bands. And if we consider the conventional antiferromagnet is some sort of square lattice, then simply this is a prime example of a TT symmetric material. However, once we consider also this non-magnetic system, so then, for example, by changing the orientation of this spin, we cannot by any translation or inversion get to this picture, right? So then we are again having the symmetry broken, and the anomalous Hall effect should be allowed. So in this most simple picture, the anomalous Hall effect should clearly distinct if we have an antiferromagnet or altermagnet. So from that perspective, and from the fact that experimentally it's relatively easy to measure, and that we do not need any interface, we don't need any injection from one material to another material, we are not so sensitive to some interfacial symmetry breaking effects, right, which will always complicate the interpretation of experimental data. So the anomalous Hall effect seems to be like a relatively readily available way how to test the altermagnetism. And one more thing which I want to mention is let's say important, that the anomalous Hall effect in ferromagnets is in principle relying only on the orientation of the spin. So it's only basically once I fulfill the correct geometry, the perpendicular to each other, I will always get anomalous Hall signal. In the altermagnets, it's not only the spin orientation, but also the crystal orientation which matters. Therefore, it already points to the fact that the mutual orientation of the, let's say, crystal arrangement and the spin will allow or not allow for the anomalous Hall effect to be present, to be non-zero. And this kind of characteristic anisotropy, or this highly anisotropic behavior, is also what makes it, let's say, distinct from the ferromagnets. And I will come back to it when we discuss the experimental part. So let me start with, let's say, I would say now one of the maybe the most explored material. It was also discussed yesterday, the semiconducting mangan telluride. It was introduced already, so I will just very briefly say that it's a semiconductor. Our samples are MBE grown on indium phosphide. And these hexagonal planes of manganese are surrounded by these tellurium cages, and the calculation show this characteristic splitting, and therefore the consequent anomalous Hall effect is allowed. And this is indeed what we did already some time ago, that on mangan telluride films we patterned to this very simple, very standard Hall bars, and in this geometry, then we apply magnetic field. Here, I just show the geometry. This is the c-axis, this is the out of plane. Here it's the AB plane, and the magnetic field in that case I show along some, let's say, arbitrary angle with respect to the sample plane. And this is simple for the fact that also there are multiple domains in this compound, and then the in-plane component helps us of the field to sort of sort, to sort of orient the domains in the preferred direction. So I will then show a little bit more of the magnetic fields, but just that you see that the magnetic field is not perfectly perpendicular, and this is the reason. So the longitudinal measurement, the magnetoresistance, it shows this sort of even symmetry. There is maybe something small happening here, but it's like a relatively conventional signal. And then when we look at the as measured data basically on the transversal signal, we see that the signal is dominated by the linear contribution, by the ordinary Hall effect, as expected for a semiconductor. However, after subtracting the linear background, simply a straight line, we immediately see that there is some signal left, and this signal has several characteristic features. So first important point is that the signal is so-called spontaneous. Spontaneous, what I mean is that the signal is present in zero magnetic field, and it has these two sort of values, two states. So it simply points to the fact that it cannot be some magnetic field induced effect. It cannot be just a effect which naturally when you apply magnetic field, then it will count the spins, and it would generate some sort of effect. So no, here we have the effect clearly present in zero magnetic field with this hysteresis. The second important thing is that the effect is sort of closing, or the hysteretic loop is closing at the field, which we know that it's the spin flop field. So it fulfills, let's say, the properties of the mangan telluride. So it can be linked basically to the mangan telluride. And the third feature which I want to mention here is that you can see that when the magnetic field is the largest signal is basically when the magnetic field is not perfectly perpendicular, so that the largest signal is, let's say, when the magnetic field is along this 60 degrees. So, and again, this is completely consistent with the observation that mangan telluride has these multiple domains, and they can be polarized by some field, and by this polarization, by the in-plane component of the field, one can sort of maximize the signal. Nevertheless, one can also see that by applying the 30 and minus 30, the signal reverses sign, which basically says that the signal is proportional to the out-of-plane component of the magnetic field, right? Because the in-plane component for the basically green and yellow is the same. However, the signal is changing the sign. Therefore, it's the out-of-plane component which matters. However, it still helps us to have also the in-plane component. So now when we see this signal, we can measure it somehow systematically. And here I just like put a very simplified cartoon. What is actually happening here is that the two states, two, let's say, spontaneous states correspond to, let's say, the same compensated state of the spins. However, having the spins pointing to different, let's say, positions in the crystal. So this is what I meant before, that the crystal, the mutual orientation of the crystal and the spins is playing the key role here. So this sort of cartoon tries to on the most simple way explain how is it possible that we have basically two different responses, two different values. And when we now look at the very simplified cartoon, also comparing it to some sort of ferromagnetic system, so in without considering any crystal environment, right, then these two would have equal energy. However, once we consider also the let's say the magnetic environment in the simplified case, we kind of can clearly see that, yeah, one can say the difference between these two, and one can sort of attribute now completely just for schematically that one of them has lower energy, one of them has higher energy. And then when one kind of shows this reversal curve, let's say in the high saturated field, this is the preferred, this is the low energy system, the low energy configuration. However, then ramping the magnetic field down, one kind of again has the spins being aligned parallel to or anti-parallel to each other, and applying higher magnetic field further, the spins are counting, but in the now unfavorable direction, and then by even more further increasing the field, the unfavorability is already so high that the spin structure decides to reorient to the energetically more advantageous configuration, which is in our schematic case now the one which points, let's say, towards the non-magnetic position, and therefore by ramping down the magnetic field again to zero, the spins have already no reason to come back to a different state. So then we achieve these two different pictures. And now when this is sort of measured systematically at various temperatures, and one can define something which I call here spontaneous effect, which is the effect which is present in really zero magnetic field, and the effect which is called saturated. And one can also see here that both of these are basically vanishing when we approach the critical temperature of the mangan telluride being around 310 Kelvin. So I will not go more into the detail with this for time reason, this system, but I just want to also highlight that this is one of the materials which also has the spin splitting confirmed by Arpes, by Juraj Krempansky and others. This is like many beautiful works around already. And I will now look in another material, and this is the mangan 5 silicon 3, where the situation is a little bit more complicated, because in bulk crystals, these are having several phases, and one of them is this collinear phase with the underlying tetragonal crystal structure, which is a perfect antiferromagnet, exactly in the definition which I said before. So it has the TT symmetry. We do not expect any anomalous Hall effect. People do not measure any anomalous Hall effect. So this is the bulk. However, when the material is grown in thin film form, it has this in thin film form on silicon 111 substrate. It stabilizes the paramagnetic hexagonal lattice, which is this silicon 111 is forming these hexagons. And as I said before, this tetragonal lattice with this square lattice, this would not break the corresponding symmetries. However, if we have the underlying hexagonal lattice, then we are changing simply the magnetic unit cell. And here again, the thing which was connecting before here, the TT symmetry, these two positions, this is not happening here anymore. So here, by any combination of the TT or PT, we cannot simply recover. The original image. So this material is simply breaking the time reversal symmetry in the electronic bands, and this hypothesis that it's indeed like staying in the hexagonal in the full temperature range because of the silicon substrate. We tested also experimentally, as shown here, by temperature dependent structural analysis, and unlike in the bulk crystal, where indeed the magnetic phase transition is accompanied by a structural transition, the thin films in the AB plane, which is stabilized by the thin film, remains constant. So the hexagon was basically confirmed. And now when we take these films, we pattern them into Hall bars. We check, of course, before the magnetometry, just to show that it's compensated to the extent that we can measure it. Hard to say what is if there is some loop, there will be for sure some small loop, but it's, let's say, the net moment is below some 10-20 millibor magneton per manganese. And this is kind of contrasting with the anomalous Hall effect measurement, which I'm already showing here. So here the magnetic field is applied in the out of plane direction. We send current and we measure voltage perpendicular to the current, and one can see that we measure a very clear, robust, spontaneous anomalous Hall effect, which is vanishing again above the critical temperature, and it basically persists down to the down to the lowest studied temperature. So this is sort of already good hint that the anomalous Hall effect here comes from the altermagnetic origin. And further evidence is that I said that unlike in ferromagnets, we expect to have a very particular anisotropy of the anomalous Hall effect. In altermagnets, again, because it relies on the combined spin and crystal symmetry and the mutual orientation. And when we, with the external magnetic field, control the spin, we also basically change the respective orientation with respect to the crystal. And therefore, we will have like some plateaus where the anomalous Hall effect is basically not allowed. And this is more or less exactly what we observed. So here is a rotation of the external magnetic field, which sets the spins to basically different orientations. And there are some plateaus where the anomalous Hall effect is basically not allowed, and then there are some kind of regions where the anomalous Hall effect is allowed, but again, it's not a smooth cosine-like variation, which we would expect for a ferromagnet-like signal. And also, importantly, when we lower the crystal quality, when we have the mangan 5 silicon 3 with, let's say, polycrystalline quality, again, we do have some, let's say, Hall effect. However, it has this cosine-like smooth variation. So it's yet another evidence that the effect, the anomalous Hall effect, and the crystal dependency or the anisotropy depends on the high crystalline quality. So probably the last thing which I will mention in this talk is that next to this anomalous Hall effect, we also decided to look at the anomalous Nernst effect. And here, just like the motivation, that it's not only general curiosity, but that we also think about anomalous Nernst effect as a one of the, let's say, effect when sufficiently strong, when we would find sufficiently strong responses, that it's a very elegant way of heat harvesting, having some heat conductors wrapping around, let's say, material which has sufficiently strong Nernst effect, would immediately generate basically the thermoelectric voltage in this very simple way, right? Because we fulfill the perpendicular geometry, unlike in some Seebeck modules. So there is some sort of motivation for optimizing, for increasing the Nernst effects, but also we show that the anomalous Nernst effect and generally spin caloritronic responses can be used for microscopy, for magnetic microscopy tool. So these things are sort of motivating us to understand the anomalous Nernst effect a little bit better. And when we already had our mangan 5 silicon 3 available, what we did is basically to pattern the devices, which we know work for the anomalous Nernst measurement, and put them on some setup where we generate a thermal gradient, which is propagating along the full substrate. And by generating this thermal gradient, we can pick up thermoelectric voltage. And here you can already see the orange, the signal which we measure. So the anomalous Nernst effect is indeed present. It agrees very well with the anomalous Hall effect. It has a spontaneous character. And we can also quantify the thermal gradient and basically compare the anomalous Nernst effect with the existing literature, with basically the full spectrum of materials ranging from antiferromagnets to ferromagnets. And we can see that the mangan 5 silicon 3 is already pretty comparable to many materials, where the highest value is naturally achieved in this great work, relying on this heavy element, let's say the atomic mass I try to highlight by the marker size. And yes, these are indeed unbeatable to some extent. However, then coming to let's say more abundant compounds such as cobalt, mangan, gallium, we see that we are already, let's say, in the same range, despite having a metallic thin film with mangan and silicon, which all things are, let's say,
Helena, you have 5 minutes. You have 5 minutes, including questions.
Yes. Yes, exactly. So I think that this is the last slide, 2 slides, and then yes, okay. And so we asked, so where is this why is actually in our mangan 5 the effect, the anomalous Nernst effect so present? And we, together with the MINDS team, looked into the momentum resolved anomalous Nernst conductivity, and they could identify basically the hotspots of the anomalous Nernst effect, not in the veil points, which are basically not present in the mangan 5 close to the Fermi level. However, in the altermagnetically splitted these pseudonodal surfaces and ladder transitions, which again show the potential of the altermagnets to optimize also the anomalous Nernst effect. And for sure there will be materials which are even more favorable than our metallic mangan silicon and could be hope for large anomalous Nernst effect. So let me now go to the last slide, basically. I will skip the last part, just we can eventually discuss it in case somebody's interested. And what I wanted to say is that the spintronics with antiferromagnets in general is blossoming field. It has large potential from my perspective. And the altermagnets are, I think, very nicely adding a lot of features which we previously saw could not be in the spin transport in compensated systems in general. And so altermagnets are now broadening the spectrum of effects which we can observe, which we can hope that they will be existing. And so far I showed these 2 compounds, the semiconducting mangan telluride and the metallic mangan 5 silicon 3, which both show effects which are allowed only because of their altermagnetic properties. So yeah, that's it. Thank you for your attention.
Start with the audience here. Are there any questions? Yes, there are a couple. First, Stephen and you.
Helena, thank you very much for the great talk. My question would be about spintronics with antiferromagnets, and from your experimental perspective, is it possible just there is a theoretical concept of spin torque nano-oscillator made of ferromagnets, and there are a row of theoretical proposals just to replace the ferromagnetic material by canted antiferromagnetic material, and is it possible from the experimental point of view?
Okay, so I'm not so familiar with this nano oscillator, so I cannot exactly. So your question is if it's a way to use the altermagnets to replace the ferromagnets in these nano oscillators. Is this your question?
My idea, not altermagnets, but at least antiferromagnets.
Yeah, I'm not so familiar with these nano oscillators, so I am a little bit hesitating to answer. So if you help me to understand what are the key features which you want from them, you probably want like a relatively low field, or what are the key parameters which people look for in these type of devices?
The main idea is to generate signal, and replacing the ferromagnetic layers, we go to higher frequencies as for terahertz with antiferromagnets.
Yes, that's definitely, yeah, this is what we mentioned, right? So that you can definitely have the higher frequencies. The issue here is that you, of course, always struggle by, let's say, controlling the antiferromagnets, right? So the thing which you like about ferromagnets, that you can with relatively moderate field somehow reverse and control, this does not work here. So I'm not sure if this is not actually a disadvantage for the...
Yeah, thank you very much.
Yeah. Sorry that I cannot have more.
Thank you very much for very nice and interesting talk. I would like to ask about Nernst effect. From a more broad perspective, how these materials are indeed promising? I mean, that, there are some very severe restrictions for materials, so they have to operate at sometimes at very high temperatures, and thermoelectric quality should be proper so that the current is sufficient. So
Yes.
do you understand already the perspective of this particular material?
Yes. No, this is excellent point, and yes, you probably know, right, that this is not somehow widely used, but I think that it very often boils down exactly to the fact that the responses are not like large, right? So that the responses are not like extremely large. However, I think that in many cases, if the response is sufficiently large or sufficiently, or it does not need to be huge, right? It can be also, so I see like two directions. One of them is really the heat harvesting, the energy harvesting. There, it's true that it's like hard to beat the Zebek modules, right? So here one would probably have to find some sort of niche application where exactly the Nair's geometry is the thing which is saving it. For example, by wrapping some blanket, right, around a heat conductor, which connected, like accumulated over the long distance of some heat, which is kind of transport anyway, would help, right? So this I can see as a niche application. But the second thing, which I think the NERS is very often discussed, is some sort of heat flux modules or heat flux detectors. And there, in principle, the signal does not need to be massive, right? It just should be there to sort of have some response of the some sort of passive detector of a heat flux. You know, when you have a freezing box, right, and you just want to see that the freezing box is having sufficiently large difference of temperature to the outside, this could be like an easy job for the Nernst effect. And here I think that the research which is ongoing is really very important and promising, because there are many materials being reported to show large Nernst effect, large, and the anomalous especially is very important, the large anomalous Nernst effects. And ideally now the quest would be not to have samples with uranium, right, which show the largest value, because usually you don't want to have like some module with uranium detecting like the heat flux. So I think that the altermagnets also have potential here, that via this kind of splitting of the bands, they could be used to search for materials which have high anomalous Nernst, which could then be used for some heat flux sensor, for example.
Okay, let's thank Helena once again for the brief.